Okay, so let's see what you guys remember about electron configuration and valencies, right? So we did talk about the Z factor, right? Anybody can remember the Z factor? Z effective?
Atomic number minus your electrons minus the valence.
Okay, so it's Z effective equals Z. And I hate this because you're going to see Z a couple other times. We start running out of letters, and so we start recycling them. So we have Z minus S, and then where S is equal equals total electrons minus valence. Electrons. You guys remember that?
Yeah.
Okay, good. So let's try this out. So let's say we have chromium 2+, and we'll do iodide, and then I minus. Okay. So let's start off with, can you guys give me the electron configuration for these three? Abbreviated, please.
Chromium 2+ would be 4s2, and well, the noble core would be argon, and then 3d5.
Are you sure about that?
I know chromium's different. I forgot.
It's 3D. It should be 3d6 if you're adding 2, right?
Are we adding 2? Wow, you guys
Dang
are
it.
rusty.
It'd be 3d2.
Okay, so chromium would be, so you're right about the core. It's going to be your AR. Does anybody remember what chromium is and how is it different?
I remember Mercury, but I don't remember anything about chromium. Wait, hold on. I have a note.
I think you went over it. I just forgot how it's different.
The exception is chromium. Hold on, it's right here. But it says it's 3d4.
Oh, wait.
I have it all written out, but I'm not seeing it.
Wait.
I didn't put the
Wouldn't
Y.
it be- I don't know. I'm confused. I'm too tired for this.
Okay, so let's talk about chromium first. So if we look at chromium, where is chromium located on the periodic table? Let me pull up
Transition metals.
Transition metals. Let me switch my. Can you see my P table?
Yeah.
Okay, chromium is right here. So 1, 2, 3, 4. So the halfway mark is right here. What is that rule about half? Half of the d orbital. You guys remember anything me saying? Anything about that? Things like to be half full or completely full. Do you remember that?
Yes.
So then what is it going to do to try to get to being half full?
It's going to try to fill.
It's going to try to fill it. So who's it going to borrow it from?
Magnesium.
It was the next
Or
energy or the energy level.
Okay, so it's going to borrow it from the 4s, right? So then chromium would be Cr. It's not going to borrow from magnesium. It's not going to take it from another metal. It's going to take it from itself, right? Because we're talking about itself. So it's going to be Ar. So we would expect it. This is the expectation. We would expect it to be 4s2, like you had said, and then 3d4, right? This is what we would be expected. But we know that that's wrong, right? So instead, because it likes to be half full, instead it goes to Cr. It's going to be, your core is going to be Ar, like you said. 4s1, 3d5.
Okay, gotcha. I get it now.
Okay, so it just takes that one electron from the 4s and brings it up and says, okay, so now my seats are full, right?
Right.
Since each one represents two, well, each seat represents 2 spots where an electron can sit. Okay, so then if I'm talking about Cr2 plus, what does that 2 plus mean again?
It's an ion.
It's an ion. What type of ion?
Cation.
Cation. Cations are what?
Positive.
Positive. So if they're positive, what's happening? Are we gaining electrons or are we losing electrons?
Losing.
Losing.
We're losing electrons. How many electrons are we losing in this case?
2.
So where are we going to take them from?
Would you take it from the 4 and then the 3 the same way?
That is correct. We would take it from the 4 because the 4 is the highest energy level, and then we take it from the 3. So then what are we left with?
3d4.
So just so we'll see it, we're going to take it from the 4 and take this guy, and then we're going to, okay? So then that gives us our 3d4. Okay? So how many valence electrons do I have?
Four.
How many valence electrons do I have?
4.
4.
4, that's right. So I have 4 valence electrons. Okay, so then if I'm calculating my S is equal to, what again? It's the total.
Total minus your valence, right?
Yep. Total minus my valence. So S is going to equal, so how many total electrons do I have?
24.
So do I actually have 24?
Well, so it would be 22, right? Because it's an ion.
That's right. So now we have 22. minus valence electrons.
4.
So then my S is going to equal 18. So if my Z effective equals Z being the atomic energy, the atomic number, minus S. So my Z is what?
24.
Equals 24 minus 18.
Yep.
So then it's 6. Piece of cake.
Yep.
Okay. So let's do the same thing for iodide. Can I erase this? My chicken scratch.
Yeah.
He's like, yeah, get that stuff off the board.
No.
Okay, so where am I going to start with the iodide? So what is the electron configuration for the iodide?
So 5s2, 4d10, 5p5.
Okay, so you're saying what's the
Oh,
core?
sorry. K krypton.
Yeah, don't forget
Sorry.
the core because I'll mark you wrong.
Sorry.
So krypton, and you said 5s2.
4d10.
4
Five.
d10
5p5.
and 5p5. Okay, well, this is a tricky one. How many valence electrons do we have?
Just
7?
7, right?
7.
That's right, just 7. Okay. So then our S value is going to be
53 minus 7.
53 minus 7. Okay, so then our Z effective is going to be
It'd just be the atomic number again, right?
okay. That is correct.
Okay.
Atomic number is
53.
minus our S. So our answer is, ooh, wow. Piece of cake?
Yep.
So if it's I minus, then what is going to be our, using krypton, our electron configuration?
Wouldn't you just put it at, oh no, you can't do that. Never mind. I was gonna say, wouldn't you just put it as the xenon? But
for the effective.
yeah.
Yep.
So then 5s2, 4010, 5p6, because you're gaining.
So then our Z effective is going to be
Yeah. Wouldn't it just be 8? Because you're
well, that's the valence electrons would be 8. And then you're right, it'll be 8. Well, would it be 8? Let's see, total electrons.
well, because you have 8 and then the 53. So
What is our total electrons now? Isn't it 54?
oh shoot.
But it's 54 minus number of valence electrons, which is now 8. So I guess it's going to be the same, huh? 46. So yeah, 53 minus 8. I mean, sorry, 46. And then that's equals to, is that right? 46 minus 8. I mean, 54 minus 8. So we have 54 total electrons minus 8, 46. So it's the same. Oh, wait a minute, 54. No, that's right.
Because it's the atomic number.
53.
Right?
Yep, it is the atomic number. You're right, 53. So it's the same. So it's still 7. Wow.
Yeah. Don't make me second guess myself, Dr. Henry.
Okay, piece of cake. Yes, no, maybe.
Yeah.
Okay. So let me clear. Okay. Okay, so let's see. Okay, so there is going to be periodic variation in elements and how they're going to behave. So there are things that we want to remember about the periodic table, and there's kind of trends that we can kind of predict what's going to happen, right? Without having to look up the actual numbers. Although all the numbers are available on P table, and I'll show you where they're available at. But there are things that we want to sit there and take into consideration. Okay, so some of these periodic properties we're going to be talking about is going to be size of the atom, particularly the radius and of ions, ionization energy, and electron affinity. Okay, so the covalent radius is basically defined as half the distance between the nuclei of two identical atoms, okay, that are joined covalently. Okay, so I'll show you a picture of it in a second. So the trend is, right, as we go down a group, so we have groups and periods, or columns and periods. As we go down in groups, our N value is going to increase. that also means that the size of the atom is also going to increase, which also means that the radius is going to increase. So as we go down, you're going to get an increase. And that makes sense, right? Because you're basically putting another ring out of electrons, and another ring, and another ring, and another ring. Have you guys seen the Russian dolls?
Yep.
Not
Yeah.
the movie, but the little dolls that you know, you have the little one in the middle, and then you put a big one on top of it, and then a big one on the outside of it, and a bigger one on the outside of it.
Mm-hmm.
Okay, so that's kind of like what you're doing in terms of going down a group. Okay, so let me show you what I mean about the radius. So the radius is going to be the distance from, if these guys were covalently bonded together, this atom to this atom, and half that distance. And that's going to represent your radius. Okay. We've already talked about the effective charge. So, so as we move from left to right, the effective charge is also going to increase. So since the effective charge is going to increase, that means that basically means that core is going to be more positive. And so your values are going to be more and more positive. That core, the nucleus, is going to be more and more positive as we go left to right. So if that's more and more positive, or the overall charge is more and more positive, so then it's going to be pulling those electrons closer to it. So that means that it's going to get smaller as we go from left to right. So that's the reason why that effective nuclear charge is going to be important. So let's look at the periodic table. And then I'll translate. So translate to English. So as we go from left to right, the radius is going to get smaller. The reason why it gets smaller is because the effective nuclear charge, the Z effect, right? That has a stronger pull as we go from left to right. Does that make sense?
Mm-hmm.
So that's why it's significant to be able to calculate that. And it basically shows you. But if you just kind of remember, as we go from left to right, it's going to have a bigger, stronger pull. So then it's going to be pulling those electrons closer to it, right? And so it's going to be, that atom is going to be more compact, it's going to be much smaller than the one that starts over here. So this guy is going to be bigger than, let's say, fluorine. You with me? Okay, so as we go down a group, so radius gets smaller. From left to right. So here, radius is going to get bigger as we go from top to bottom. It's not Tom.
Dr. Henry, all I could imagine was who has the bigger booty.
That's right.
That's all I kept thinking. And Jessica was laughing at me during homework.
Okay, so who has the bigger booty? Who has the biggest butt in the block?
Francium.
Francium. Who's going to be the smallest? Helium.
Helium.
Helium. Okay, piece of cake.
Yeah.
Good. And so that now you guys know why that Z effective is important.
Mm-hmm.
Okay, so here, this is just basically showing you that data. Does it hold up? And are there exceptions?
There's always exceptions.
Yeah, and I'll tell you one of them that'll point out, it'll just blare itself out to you. So nitrogen and phosphorus are exceptions.
Why?
Why? Good question. Why? I have no idea. Actually, there is a reason why. We'll actually get into that when we start talking about how it actually behaves itself. Okay, so in this case, you'll see that carbon actually is a little bit smaller than your nitrogen, but then nitrogen is bigger, and then you get smaller as you go left to right. And then here we have silicon behaves perfectly, and then phosphorus gets a little bit crazy and then gets a little skinnier than sulfur. So and again, all of these values are available on your periodic table, and they're going to be important later on when we start talking about calculating lattice, depending on who they're bonding with. You may have a different radius, and they'll be important for calculating how much energy is going to be needed to maintain that structure.
And calcium's also an exception.
Yes. Yes. Yeah, but there are always going to be a couple of them that just kind of screw everything up.
Okay.
And you'll start noticing it primarily down here as well too. When you get to that energy level where you're starting into that 4s component. Okay, questions, concerns, Cash. But for the most part, there is that general trend. Okay.
Calcium, phosphorus, and nitrogen.
Yeah.
Are all the exception.
They're not all the exceptions. There's a few more, but those are the main ones that you should
have
be aware of.
Mercury too.
Yeah.
Mercury looks like it doesn't follow.
And look at BE.
Yeah. That was that strontium or whatever underneath calcium.
Yeah. So there'll be a few of them that don't follow it. And you can actually look at the values. And I'll show you that on PA table real quick. It's valuable later on when you're calculating lattice energies and when you guys are on to your next gigs. So the way that you would find the radius, and again, these are calculated radiuses. There are a few that are experimental.
And these are the exception to the radius size?
Yep, those were exceptions to the radius size. So this will show you the general trend. Clear. Right? So if you look at it, your maximum values, and then your minimum values. Okay, so if you wanted to look at the radius of, let's say, fluorine, it's right here, radius. This will give you your covalent radius. That will be your empirical radius. And that will be your van der Waals radius. All those are going to be important for anything, but the calculated radius is what we're going to be using for calculating, like I said, lattice energy. Let's see, erase, clear. Okay, questions? Good. Okay, I like it when there are no questions. It means that you guys either get it really well or you have no clue. Okay, so this is just showing you a table and just the general trend. All right, so again, helium the smallest, and as you go up, then lithium is pretty big, and then it goes down. Neon is pretty small, so on and so forth. Okay, and then you'll see period 4, those transitional elements. Oh, they kind of a little crazy, and then we got those kinks right there. And you'll notice, like I said, you'll have a few of them that break the rule, but for the most part, general trends. Right? Okay, so we've talked about Ionic radius is just basically described as the measurement used to determine the size of the ion. Now, this is where the Z effective charge is going to play a part in it. And you're going to kind of use that to determine whether or not you're going to be closer than the the element itself, right? So like for instance, if you have a cation has fewer electrons, but it has the same number of protons. So you would assume that the effective is going to be larger or smaller. Anyone want to take a guess?
Will you repeat the question?
I said, since cations have fewer electrons, but the same number of protons, we would assume that its Z effective would be larger or smaller?
Smaller.
Smaller?
Mm,
Would the atom be smaller or would the atom be larger? I mean, the ion be larger or smaller? So are we changing the number of protons?
no.
So we're not changing the number of protons, but we've gotten less electrons that are going to be in our way, right? So if we got less electrons that are going to be in our way, so wouldn't we assume that our Z effective is going to be greater? Yeah, no, maybe.
But
If you have fewer electrons, then you're not taking away as much, so it would be greater.
Okay. So then it would be greater. And so that also means that we're also going to be pulling what? It's going to be pulling the electrons closer to it because you have less electrons than protons. So it's going to be pulling much closer. So you would assume that a positive ion or a cation is going to be smaller than, let's say, a normal or a parent atom. Does that make sense? So
Yeah.
if we have Cr 2 plus compared to Cr, who's going to be bigger in size? Who's going to have the bigger butt?
CR.
Cr is going to be bigger, right? And this guy is going to be smaller because the electrons are being pulled closer to it, so it's going to be more compact. You get that, Cassie? Yeah, that look.
yeah, that's what I was thinking, but I was hearing opposite. So
Okay. Okay, so an anion, what would you expect for an anion?
larger.
We'd assume that we get larger, right? So in most cases, it's going to get larger, although there are exceptions, right? Everything, as we're finding out. So we'd assume that it would get bigger because then you have more electrons than you have protons, and then it's going to behave funny that way, right? Okay, so cation is always going to be smaller than the original atom, and an anion is always going to be larger than the original atom. Okay, questions, concerns, Ash? Credit? Okay, here's an example. So we have Al, and then we have Al3 plus. Right? So Al is going to be bigger than the Al3 plus. Here we have S and S2 minus. S2 minus is going to be bigger than S. Oops. Okay, so the next thing is isoelectronics. Isoelectronics, basically the simplest way of thinking about it. What does iso mean? Isothermic. isotonic. I don't know what else iso.
They're
Same.
all equal.
It means the same or equal, right? So we're saying that it has the same number of electrons, essentially. Isoelectronic means the same number of electrons. So you're looking for ions and atoms that have the same number of electrons. So like, for instance, all of these guys are isoelectronic to neon. So this is the electron configuration for neon. It has the same number of valence electrons, same number of electrons as neon. So N3 minus, O2 minus, F minus, sodium plus, magnesium 2 plus, aluminum 3 minus. All of those have this electron configuration, right? And they're all isoelectronic to neon. Okay, so if they're asking you for isoelectronic, you want something that's going to be the same number of electrons. Also, okay, here's a question for you. Since they're isoelectronic, are they going to be the same size?
No.
Okay, so who's going to be bigger?
I would assume the one with more electrons.
We'd assume the
Well,
one
and
with-
closer to the francium, or which is the bigger radius.
Okay. Okay, so the one that would be closest to, okay, so here we have, let's go. So we know the general trend, if we're just looking at the atom by itself, fluorine would be, or sorry, neon would be smallest, right? But here we know that this guy, since it has one less electron, that means it has more positive charges. So then this guy would be pretty small, but then this guy would be pretty small. But this guy should be even smaller since it's lost 3, right? So we assume that this guy would be the smallest, and then who would we assume to be the largest?
Nitrogen. The nitrogen ion.
That's right, the nitrogen ion. Okay, does that make sense?
Yeah.
Okay, good. Ionization energy. Okay, so for ionization energy, ionization energy is just the energy to remove the very first electron. Okay, so we're looking the amount of energy that's required to remove that very first electron. That's your first ionization energy. The second ionization energy is the energy required to remove the second electron. To remove the second electron. Okay, and then the third ionization energy would be the energy that's required to remove that third electron. Okay, so the way that ionization energy works is, so ionization energy is going to increase across periods. So as we move across from left to right, it's going to increase. So the amount of energy it takes to remove an electron is going to increase as we go from left to right. So if we think about it on the periodic table, we have sodium. So we assume like sodium is going to be pretty weak, it's going to be really easy to remove. But then fluorine, is fluorine going to want to lose an electron?
No.
No, fluorine wants to gain it, right? So it's like, no, you're not taking my electron, so it's going to fight it. And then as we go down, right, ionization energy is going to decrease. So it's a lot easier to remove an electron from francium. Francium is like, it got so many electrons, I don't care. Don't, it'll drop it off the side of the road because it's so big, you can't keep track of all of its electrons, right? Because its butt's so big, right? Okay, are you guys good? You're with me?
Yeah.
Yeah.
Okay, so this basically just shows you the ionization energy. All right, and so as you can see, we started with hydrogen and helium. It's a lot harder. Helium is the one that has the highest ionization energy on the periodic table. It takes a lot of energy to remove that electron. And then this basically shows you on the periodic table, ionization energy. If you actually want the values, you can find that here as well too. Where's it? Ionization energy. Okay, questions, concerns, Cash? Okay. Ooh. Let me see. And of course, we have people who break the rules, right? Got some rule breakers. So boron, beryllium is an example of a rule breaker. So it takes more energy to remove it from beryllium than to remove from boron. And so part of that is because you're going from that increase in your subshell, right? So you're going from that S2 to that P2, right? I mean to that P. And so it's a little easier because it's a little easier to get rid of this guy because this is already cool, right? Because this guy is already kind of happy. It has those 2 electrons. It's like, okay, I'm cool with that, right? I'm cool with having those 2 electrons there for right now because I have one in both directions. Where this guy, it'll be easier to remove from boron because it has just that one guy by himself. He doesn't have 2 others to kind of keep him in check. So that's part of that reason. Remember when I talked to you about it will prefer being half full than, and part of that is because this takes more energy. So it's anxious to kind of get rid of it if it can, that electron, because you just have that one electron in that p orbital. Where these guys are going to balance each other out magnetically by going in opposite directions. Okay, do you understand what I'm saying there? Yes, no, maybe?
Yeah.
Kind of, yeah.
Kind of, yeah. And so you'll see that generally as we move across. Another deviation is oxygen has a lower ionization energy than nitrogen. Nitrogen, again, you'll notice that nitrogen has a lot of deviation. So, okay, questions, concerns, Cash?
Nope.
Okay. Okay. And the nitrogen component, right? So this is oxygen. And if we remember, nitrogen would be this. Nitrogen is half full, right? So nitrogen is like, I'm cool with being half full because everybody's happy here. I don't have this like random extra electron here. So its energy, ionization energy is going to be larger because he doesn't want to get rid of that half full. Right? It's like, I made it this far, I'm not going to give up now. For oxygen, it's like, yeah, I'm cool with, giving up this little bit. It takes energy, but it doesn't take as much energy as it would take to remove an electron here. Okay. So are you with me? You see how those deviations exist or why?
Yeah.
Okay. So as you get rid of that first one, the ionization energy typically is a little bit greater for the next one, right? Of course, depending on who you're talking about, right? So let me give you an example. So we have potassium. So this is the ionization energy for removing from potassium, it's 1 electron. But if you try to remove that second electron, look how high that goes up, comparing the two. First one, second. And so generally the trend is the second ionization energy is greater than, it takes more energy to remove the second electron than it takes to remove the first electron, generally. Okay, questions, concerns, yeah. Okay, so electron affinity is the affinity to try to get an electron. So who do you think is going to have the highest, who's going to want electrons more?
Isn't it the ones right next to the noble gases?
That's right, those are called
Halogens.
halogens. Okay, so halogens are going to want electrons more. So they're going to have a higher electron affinity, and so their value is going to be positive, where those elements that want to release, that want to get rid of an electron, they're going to have a lower electron affinity. Okay, all right. Okay, so this process is going to be endothermic or exothermic, which kind of makes sense. Also means that either you're going to be putting energy into a system or you're going to be removing energy from a system. So actually, the electron, I'm sorry. Let's see. So if we look at electron affinity, right? So noble gases, they're not going to want to take anything. But so group 1, these guys are going to have, in terms of wanting to take an electron, they're not going to be so keen on taking an electron. Their values are going to be lower. It's going to be low, but not as low as these guys. So you can see here, these guys have a higher negative value compared to, let's say, the lithium and all those guys, because they don't want to take it. They actually want to get rid of it. It's not going to take a lot of energy to sit there and for them to take it. And then as we get to like group 2, then those are positive values, right? So basically you got to put energy into that system rather than energy being released. And the concept is that these negative values represent energy being released. So it's going to be favorable to lose electrons, or I mean to gain electrons, which here is not so much, not really favorable compared to these guys. Much favorable. A lot of energy is going to be released to sit there and do that. And then again, if you take a look, who's our exception in this trend? So if we go from beryllium, any exceptions that you guys see?
Nitrogen.
Nitrogen. Okay, so nitrogen is an exception for this as well too. Questions, concerns, Cash? Good. Okay, so that's chapter 6. Chapter 6 was a long chapter. So what are the things that you guys are going to be expecting from chapter 6, from the exam component?
Can you repeat that? Sorry, I didn't hear.
What are the things which you expect for the exam component for chapter 6?
Electron configuration.
Oh, yeah, I was about to say.
Okay, obviously electron configuration.
Hund's rule.
Hund's rule,
Quantum numbers.
quantum numbers.
Wait, are you asking us to basically give you ideas for the exam?
Yeah, I'm just asking you.
No!
Well, don't worry, I have my own ideas, but we'll see how well you guys remember what we talked about.
I assume electromagnetic radiation too.
That's right.
So basically everything we've learned so far.
That's right. So you're going to be able to calculate the amount of energy that's being generated from photons and things to that extent. Yeah, no, maybe.
Maybe.
And then you should be able to also calculate the number of moles, the moles of photons that are generated to do that. Is that correct?
I guess.
Okay. Good.
I'm panicking.
You always panic.
I know.
Okay, so let me pull up the next chapter. Oops. Okay. So this one we're going to go pretty fast through. Slow me down if you need a little help, but it kind of deals with all the stuff that we've learned already. Let's get it started. Can you see my slides? Okay, good. Good. Okay, so basically we're going to be talking about ionic bonding, covalent bonding, Lewis dot structures, formal charges, resonance structures, strength of ionic and covalent bonds. We're going to be talking about structures and polarity. Okay, so if you guys have me for 2A, you guys should remember all of this because we talked about all of it. But I think over 3 chapters. Okay, so what is an ionic bond? Do you guys remember?
The non-metals, right?
Ionic bond or nonmetals?
Are there?
Are you sure of that?
Just kidding. They're formed by ions.
So they form ions. So it's 2 ions that are coming together to form a bond, right? So like for instance, we have sodium metal and we have chlorine gas. So when sodium and chlorine gas come together, they form salt. Is that true? NaCl, right? So what do we know about that sodium? What does it want to do, that sodium metal? Anyone?
Lose electrons?
It wants to lose an electron, right? So it wants to go from Na to Na plus, because why does it want to lose an electron? Do you remember?
So it could be like a noble gas.
To be like a noble gas. Now remember, everybody, because the noble gases are stable. Why do we want to be like noble gases again? What does nobility mean to you? What does nobility mean to you, Matt?
Nobility?
Nobility.
I think you asked me this last summer and I gave you the wrong answer.
There's no,
I think
just
of
tell
noble as like, I don't know, like faithful or like trustworthy or.
So you think of noble as being faithful and trustworthy? So like, did you ever watch, let's see, where's that show called? Game of
Or
Thrones.
like a noble steed.
A noble steed? Okay, so
I
noble
don't know.
steed. The
like a
Game of
Groot.
Thrones. have you ever seen like the ancient King Arthur times or kings and queens?
Mm-hmm.
Right? So aren't the people that are like right underneath the kings and queens called the nobles?
Yeah.
So why are they so noble? What makes them noble? Is it because they're faithful and they're loyal and they're
No.
so in terms of the caste system? So caste system, you have the poor people and then you have the noble, right? On top. So what makes them different between poor people and nobles?
They're poor.
Poor people are poor and nobles are typically rich, right? They have
Yeah.
money, they have land, they have value, right? They
Uh-huh.
have, if we boil that down, they have stability. They have a roof over their head, they have cash coming in. They're good, right? Why are you guys going for careers? Is it because you want to save the world? Or is it because you want to be able to sustain yourself?
Both, right?
Well, in theory, both, yeah. So a lot of us are doing it for both reasons. But if we boil it down to it, at the end of the day, it deals with money, right? So if let's say I was a prince from Zimbabwe, right? I had millions and millions of dollars. And Abby, I come to you. Abby, you're beautiful. Your smile just makes me happy. I'll give you half my kingdom if you marry me. What would you do, Abby?
I don't know.
Oh, come on.
I couldn't hear the last part. You went like,
I went too fast.
yeah.
Okay, Sadie, what about you? What would you do? You'd be like, hell yeah. I'd be like, okay, where do I sign? You know, I wouldn't even blink an eye. I'd do it instantly, right? Because you think of it, you're like, okay, I have stability. There's finances, there's a kingdom, I have people serving me. Hell yeah. Wouldn't even blink one eye, right? Let's go. Let's do it right now, right? So at the end of the day, it's about stability. Now that's the same thing with these elements. All these elements look up to the noble gases and they're like, dude, you're stable. How can I get like that? So there's three ways of getting like that. You could either give, give away an electron. You can take an electron, or you can share, right? So a lot of us, if we can't do it on our own, we find somebody else who can do it and we marry them, right? You heard of gold diggers, right?
Yep.
Right? So we should make a TV show called Gold Diggers, right? Or is that the housewife of Orange County or whatever, you know? So in that sense, you know, that's the same thing that's happening with these elements. Sodium, right? Sodium can get rid of it, right? It's like, okay, I have an extra one, let me drop it. Chlorine is like, hey, I need an electron. It needs, actually, in this case, it'll need two because it's diatomic. And so it's going to take that electron that sodium drops, right? So then sodium becomes plus, and then chlorine becomes minus, and then they're like, oh, you're plus now, and I'm minus, we can get together, we form a power couple, right? To form sodium chloride. And this is an ionic bond because they're both charged. And what's holding them together is one is positive and the other one is negative. Ionic bond. So you have electrostatic forces of opposite charges coming together. You have your cation and your anion coming together to form that power couple. Okay, now this bond here between sodium, the sodium ion, sodium cation, and the chloride anion is a strong bond, right? Long as there's nothing to kind of disrupt them or anything like that, like water. You know, water is a homewrecker. Okay, so it's going to be a strong bond between it. So it's going to be really hard to sit there and separate them. It's going to take a whole lot of energy to sit there and separate those ionic charges, unless you add it to water, right? Put something in the middle of it, yeah, breaks up any relationship, right? That's why threesomes and open relationships never really work out. Okay. So, questions?
Nope.
Okay, good. Okay, so let's talk more about this ionic bond that's forming. So we have these ionic bonds that are forming. So when they're solids, they come together, they form what we call crystalline structures. So they form nice crystal lattices. So these charges also prevents them from moving freely. So they're often going to be rigid and brittle, right? So you think about salt. Have you guys seen a block of salt? Rock salt?
Mm-hmm.
Okay, now if you sit there, you can crush it, right? But isn't it pretty rigid and brittle? You can't just sit there. It doesn't just like melt in your hand or anything like that, or malleable or anything like that, is it? Pretty brittle and rigid. They have high boiling points, high melting point. They horrible at conducting electricity as a solid. Now, as soon as we put it in water, oh, they're all happy. They're separated, you know? And so they're able to conduct electricity with no problem. But as a solid, if you stick, you know, your electric cables in salt, you're not going to get any electric conductivity. They're really poor conductors of electricity. So this here basically just shows you the boiling points and the melting points. You see it. So, and there's like a general trend. So we have lithium, sodium, chlorine, and of course, there's always going to be a couple of exceptions. If we take a look at where lithium, sodium, and chlorine, I mean, potassium is at, sorry, lithium, sodium, and potassium, you know, lithium is higher on that ionic scale. So typically it's going to have a little, you know, it's going to be pretty strong in terms of that bond that we're having, right? The energy that it takes to melt it, to sit there and to, or cause that to boil, okay, its melting point is here, boiling point is here. So it's going to take more and more energy. So this is degrees Celsius, 610 degrees Celsius. Right? Isn't that pretty big?
Yeah.
Could you imagine being 600 degrees Celsius outside?
I'm
It'd
good.
burn off our skin, right? We wouldn't exist at that. So it takes a lot of energy to sit there and just to sit there and to change states. That's just changing states. That's not even separating or breaking those bonds. So that kind of gives you an idea of how much energy it's going to take to sit there and break those bonds, that interaction, that ionic bond. Okay. Are you with me?
Yep.
Okay. Oops. Okay, so we've talked about first ionization energy. This is just a nice little table showing that. And we've also talked about electron affinity. What is ionization energy again?
How much energy it takes to remove it?
How much energy it takes to remove it. Okay. So first ionization energy is the energy to remove one electron from an element. Okay. So, and electron affinity?
How much energy it takes to gain an electron.
How much energy it takes to gain an electron. Okay. Okay. So metallic elements basically have low ionization potential. Basically, they have low ionization energy compared to let's say, fluorine. So if we take a look at lithium compared to fluorine, so it's 520 compared to 1681. Non-metals or non-metallic elements have a relatively high electron affinity. Comparison, non-metal or metal, right? You also notice that as we go down the periodic table, for ionization energy, the ionization energy gets lower, right? And that's the same thing that happens going down. So that's general what we saw with our general trends earlier, right? Okay, so that means basically non-metals are really they're raring, they want to gain an electron, where metallic elements, they want to lose electrons. Make sense?
Yeah.
Okay. So at the end of the day, when they come together, they have to be neutrally charged, right? So that means your pluses and minuses are gonna have to balance out. So we know that magnesium is gonna form what type of ion? How many electrons does magnesium want to lose to be like a noble gas?
2.
So then it's going to be a 2+, right? So if I'm binding with fluoride, which is at Fi-, how many fluorides am I going to need to balance it out?
2.
Okay, so then my ionic compound is going to be MgF2. Piece of cake, all the stuff that you guys did last semester, right?
Yep.
Okay, questions, concerns, Cash? Good. Okay, so here we have aluminum oxide. Can you show me the ions that are going to be forming, or what are the two ions that are coming together to form aluminum oxide?
You want to write it?
Yeah. Now, I just want you to look at this page and just see its glory.
Ha 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 ha.
Okay, so then what would be the chemical formula for aluminum oxide? Okay, so yeah, this brings us all the way back to that very first first chapter last. I think it's almost the same time it took us to go to chapter 7. Okay, so can you guys do the same thing for these guys as well? Yes, no, maybe?
Yeah.
Okay, good.
Right now?
So, yeah, go ahead and do it right now. I'll give you 2 minutes because you should be whipping these out like hotcakes.
What?
2 minutes. It shouldn't take you more than 2 minutes. These are easy. Okay, you ready?
Oh, I need
What
2
are-
more.
Ion for lithium oxide. Anyone? Selena,
I have
Yes.
ions for lithium oxide.
I got Li2O.
So then we have Li plus, O2 minus. Okay. What about the second one? Magnesium nitride. Matt,
G3N2.
Sadie, aluminum sulfide.
Al2S3.
Okay. Abby. Boron chloride.
B C I.
Is it I?
Well, L.
Oh, okay.
L. It looks like an I.
L what? Did we lose you, Abby? Are you there, Abby? Oh, she wrote it in the chat.
She typed yeah.
Okay, so what would be the subscript? Excellent. Okay, Kayla. Are you there?
Oh, yeah, sorry. Muted myself. Calcium 3, phosphorus 2.
Piece of cake?
Yep.
Should be. Okay. Clear. Okay, covalent bonds. So covalent bonds are when you're sharing between two atoms, right? So, and these are typically done with atoms that are similar in terms of attractivity to electrons, how attractive they are to electrons. So basically, all of our nonmetals, they're going to form our covalent bonds in most cases. There are going to be some exceptions, as with everything. So again, these guys are going to be electrically neutral, right? So they're not going to have a charge that's going to be associated with them. Although we can form polyatomic ions with ionic cases, but they're going to be neutralized by other things. And the electronic charges are going to be weaker than that you see with the ionic, right? So you're going to have like partial charges, not complete charges. Okay. They're going to have lower melting temperatures. They're going to have lower boiling points. Many of them are going to be liquids, gases at room temperatures. Some cases you're going to have some solids, but these solids are typically going to be soft, softer than, let's say, our ionic compounds or ionic solids. They're going to be horrible at conducting electricity. Okay. So an example is hydrogen gas. Okay. So here's an example where we have two hydrogens that are going to be coming together. This is the energy that is needed for them to come together. So if we had hydrogen separating on its own, it would require this much energy, 436 kilojoules, to sit there and cause hydrogen to sit there and be separate. And this is not a favorable state. You always want to have the lowest possible energy. And the goal is to try to keep low energy. So that's the benefit of like the noble gases. They're kind of low in energy, right? So hydrogen forms a diatomic because it's much lower in energy than having just the hydrogen atom alone by itself. Okay? Are you with me?
Yep.
Okay, good. So we have two types of covalents. One is called pure covalent, or also called nonpolar covalent. Pure covalent basically means that you're sharing evenly, or nonpolar covalent, meaning sharing evenly. So you have even sharing between two things. So like, for instance, the diatomic molecule, hydrogen gas, is sharing evenly because both of the hydrogens have the same amount of pull. associated with it. And we're going to start talking about this pull in terms of electronegativity. Okay, so polar covalent basically means that one is pulling greater than the other, right? So in the case of hydrogen chloride, chloride is only one away from being a noble gas, so it wants to have the electron towards itself more than hydrogen does. And so the pull is going towards the chloride. So that means that the electron is going to spend more time around the chloride. How many of you guys have siblings?
Oh,
Yep.
Yep.
I know Teddy does, right? Okay, so so I know Matt has a twin sibling, right?
Mhm.
Okay, so in that case, Matt, you and your brother are kind of like hydrogen, right? So there's two hydrogens diatomic. You guys are, in theory, evenly pulled because you guys are twins, right? So you're almost like genetically, you're almost the same. And if you guys did exactly everything the same way, you'd have the same strength. And you know, so you'd be even. Right? So you'd have even pull with each other. Okay. So how many of you guys are older siblings? Lady, are you
well, we
the
know
oldest?
you are, Dr. Henry.
Oh, I am. Yeah, I definitely am. So I have two sisters, right? Two younger sisters. So when we got toys, right? Things like PlayStations or anything like that, although they weren't PlayStations when I was growing up, it was an Atari, right? So we got an Atari. And so the rule was, right, we had to, my parents said, okay, we're getting this. It's a gift for all of you guys. That was the only gift that we got, other than socks and underwear and stuff like that. So we had to share it. So my philosophy of sharing was, I get it 90% of the time. My sisters get it 10% of the time when my parents were home, right? So when my parents weren't home, I was playing Atari all day. Oh, get away from me, just knocking them off and stuff like that. 5 minutes before my mom gets home, then I give the Ataris to my sisters to play, right? So that was sharing, right? Is it not sharing? They get to play with it.
It's the uneven sharing.
It is the uneven sharing. So that would be an example of polar, right? Polar meaning uneven, bipolar, like, so one is getting it more than the other, Okay. Are you guys good with this so far?
Yeah.
And we've talked about it. This is all kind of recaps. So what determines and also helps us dictate whether something is polar or non-polar is called the electronegativity. Now, it's not to be confused with electron affinity. Electronegativity is like this arbitrary number that is based from 1 or basically 0 to 4. 4 being the highest, 0 being the lowest, although there's nothing on 0. So you're going from 0 and all the way up to 4. Okay, so things that are more electronegative, such as fluorine, they get that 4 value. And then, so it's based upon, so this guy named Pauly, right? So he basically, he came up with these values, and he actually tested them out and to kind of get an idea relative to each other, right? So fluorine has a stronger electronegativity, meaning that it's going to want to get an electron as much as possible, right? So if we're going to share, fluorine is going to be like the bully. He's going to be like, I get it almost all the time. You can get it a little bit, but I'm getting it most of the time. And we're going to share, but I'm getting it most of the time, just so you know. And he's always going to be like, okay? And then, so all of the halogens, their electronegativity is going to be higher than their neighbors, right? So if you're on the same period, their electronegativity is going to be higher. You'll notice that oxygen is 3.5, but chlorine is 3.0, right? So when these guys come together, then oxygen is going to be like, hey, I'm the big one here, right? But I'm going to get it most of the time. You're going to get a little bit of the time, okay? So are you with me there?
Yes.
Yeah.
Okay, so the way we have ranges, right? So we say things are pure covalent if they're basically there's no covalency. We'll say they're non-polar covalent if they fit within a certain range. Okay, so let me give you the range for your book, for your chapter. Okay, so for your book, it says if it's greater than 0.4, okay, then it's considered to be less than 0.4. It's able to be considered to be purely covalent. What I mean by it's less than 0.4, the difference between the two elements that we're looking at. So if we're looking at two carbon elements together, that's going to be 0, right? So that's going to be less than, that is going to be less than 0.4. So it's going to be pure covalent. It's going to be polar covalent if it's between 0.4 and 0.8. And then I'm just going to give you a little more guidance here. Okay. And then if it's greater than 1.8, then it's considered to be ion. Okay. Good, bad, ugly. So if we're talking about, let's say, carbon and hydrogen, right? Let's go back to that table. Carbon and hydrogen forming a bond together. Is that going to be covalent? I mean, is it going to be pure covalent, polar covalent, or ionic covalent? Here's hydrogen, here's carbon.
So you just take the difference of the two?
Yep.
Okay.
So you got 2.5 minus 2.1. That's going to equal what?
That's pure covalent.
So is that going to be pure covalent, polar covalent, or ionic?
Pure covalent.
Pure covalent. Okay. What about oxygen and oxygen and chlorine?
It would be the other covalent, polar covalent.
That'll be polar covalent because it's 5, right? Okay. Okay, we're gonna stop here. We'll pick this back up on Wednesday. So make sure you guys are doing your simulation and then start building your spectrometer. Okay,
Okie dokie.
I'll talk to you later.
See ya.
Bye-bye.
Bye.